some language that you have to understand. So the logical address side, we break it to pages. In fact, we call that logical pages. And on the physical side, it's called frames. So here we've got a bunch of frames, and on the logical side, it's called pages. We also keep track of all the free frames, where they are inside our computer. And to run a program of size n pages, then we need n free frames and load that program. So if we take our computer process and break it up into smaller chunks, each chunk is a power of 2 chunk, then we need so many chunks available inside our main memory. We have to set up what we call a page table. This is the magic that makes this work. So apart from the MMU, the physical hardware, this MMU goes and looks at a special block in memory called the page table that houses this translation. The backing store likewise is split into pages, and we still get what we call internal fragmentation. And this brings me to how this works. As you can see, I'm moving away into Excel, which means note, important. Okay, so here we have an example of a hypothetical 8-bit computer. Right? This 8-bit computer has 8-bit physical memory, so it's not a lot of memory. Very, very small, right? But the principle is explained. What you see here is our page table. Our page table, in this example, we're only using these 4 entries here at the bottom. Page table contains what we call indexes, from index 0 to index, in this case, index 7. But effectively, we're only going to use 0, 1, 2, and 3. These indexes explain which page frames we're going to work with. And these page frames basically, this page table has entries in there. These entries is either a valid bit that says that it's loaded in memory or not loaded in memory, and it may have a value. In this case, it has some binary values. Can you see the binary value of index 2 is? What is the binary value of index 2? 0. What is the binary value of index 3? 1. What's the binary value at index 1? 2. 2. Binary value at index 0? 3. And that can be anywhere. Okay? So that they don't have to be in this order, they can be anywhere, in any order they like. Right, now how does this work? So here we've got a logical address of 246. So our computer says, I want to go and access the instructions in my program counter hypothetically. I'm going to load the next instruction as logical address 246. That's the decimal value. When you translate this decimal value, this is what we get in binary. Those 8 bits. Make sure, this is very important, make sure that your number is always 8 bits. How do you get a small number, so let's say 11, how do you make that number 8 bits? Add a bunch of zeros in front of it, then to the left. So that's very important. Make sure it's always 8 bits. Why is that important? It's because your 2 most significant bits, in this example, plays an important role. And if those bits don't exist, then this thing doesn't work. And so you have to know what the value, even if it's 0, 0, it is still the value. So what do we do? When you see that this is our binary number, let's write it here, 1111 space 0110. That is the binary number. No why that happens. Okay, let's something else. 1111 010. Okay, anyway. Note the left 2 bits. What is the left? So what is bit number 6 and 7. So if we count from bit 0, 1, 2, 3, 4, 5, 6, and 7, it is 1, 1. That's the most two significant bits. That is what we call our page frame value. Actually, the index, that's the index of it's basically the page frame, and it allows me to look up the index here. Now, just looking at those two bits, sorry, who doesn't understand where I got 1, 1, 4? Okay? The left two bits, left two most bits in your 8-bit number. 8-bit number. Remember the answer, the question said 8-bit computer. So the bits number of the two most significant bits. So by the way, when we've got that, what is left? So let's just write the rest of the binary number. So up to 0, 1, 1, 0, 1, 1, 0. So if you put these two together, we have this number. Okay, so that is the least significant bits, the 6 least significant bits. These are the two most significant bits in this example. This is what we call the offset. Those least significant bits. That's the offset. This is the page frame. That is, what is the value in decimal of 1, 1? 3. That's 3. Okay, so let's go and look at index 3. The index 3 is that guy there. So we go to our page table at index 3 and we look up our page frame there. Page frame number 0, 1. So now you go to your offset. There's our offset, and you add 0, 1. Sorry, actually you replace, maybe that's a better word. You replace the two most significant bits with the page frame bits. That's what happens here. And this is exactly what happened in this case. So there is 0, 1, 1, 1, 1, 0, 1, 1, 0. I didn't write the 0 in front, but that's effectively what happened. Who's lost? Who doesn't know where I got 0, 1 from? Okay, so that then translates back to the physical address of 1, 1. So just a few notes here. This was the offset. We got frame number 1. Why is it frame number 1? Because 0, 1 translated to decimal is 1. And that is where that gets added to the front of the offset. That's our new address. This is what the MMU does for each and every new person. Yes?
We create the webinars, right?
Yes, for your test.
What could you
What could change?
What could you set as
Okay, so things that can change is this. I can put that at 0, there. And let's take that as an example, and I can use another number. In this case, logical and physically translate to exactly the same number. Why? Let's figure it out. From 148, that's our logical number. Translate that into binary. That's 1, 0 is the two most significant bits. That's index 2. So go to index 2, read out what is the frame number, 1, 0, add that to the front of your offset, exactly the same. So in this case, it's not a great example, but it can happen. It is possible for the logical and the physical to be the same. But this basically explains what happens in the MMU. So the MMU basically filters, looks at the binary number, breaks up the binary number into two sections. One is called the page number, the other one is the offset. Page number, they look that up in the page table, get the resultant frame number, get the frame number, add that in front of your offset, and that is then your address that you want to physically back to. Yes.
In a test, do we have to show the page number, the frame number, and the offset?
So in a test, you will be given that question. So convert the following 8-bit logic into 8-bit physical address. I expect you to show me. So the reason why I ask you to show me how you get to the answer is because students cannot convert from decimal to binary. That is a reality. So that's the first thing I want you to do. Show me how you convert that number